first thing, that is, so topic whatever we are discussing is heaps and heap sort. Heaps and heap sort. So what is an heap? So heap is a partially ordered data structure, and this is usually suitable for implementing priority queues. So it is partially ordered data structure, and what is the application of this heap sort? It is used in implementing priority queues. Used for implementing priority queues. So this heap can be defined as a binary tree. You know what is meant by a binary tree, right? What is a binary tree? What is a binary tree? In your own words, you reply. What is a binary tree? Yes. What's a binary tree? No one knows what is a binary tree. You would have taught these things in the data structure. Reply.
A tree which having both left and right of you.
How many nodes a binary tree can have? How many maximum nodes a binary tree can have?
2.
Yes, 2. 0, 1 or maximum 2. Isn't it? Yes. A tree which can have at most 2 nodes. Himabindu replied. So she says that it's a tree with at most 2 nodes. That's true. And it doesn't mean that it should have 2 nodes. It can have 0 also, 1 or 2. Maximum will be 2. So that's what at most means. So binary tree with at most 2 nodes. Now, so heap is defined as a binary tree with keys assigned to its nodes, and some of the following conditions should be met. Okay, it requires a tree shape. It should have a tree shape with the following requirements. What are the requirements for that? It should form a tree shape. It should have a tree shape. What is this tree shape? Binary tree shape, wherein this binary tree should be complete. What do you mean by complete binary tree? You know the difference between complete binary tree and full binary tree? Now you don't search now, Google now, okay? You should know these things. When you say binary tree is complete, let me write an example for you. Is this tree a binary, complete binary tree or full binary tree? Look into this tree. Is this a complete binary tree or a full binary tree?
Complete binary tree.
Yes. How do you say it is complete binary tree? Because a complete binary. Yeah. Yes. Continue.
Every level should be filled except the last one.
Yes. Every level except until the last one level.
Except last level, all the levels are filled completely, ma'am.
Yes. Full binary trees, all the levels will be full, completely filled. A complete binary tree is one wherein the last but one up to last but one level, all the nodes will be filled, but last level it can be incomplete, provided that the nodes will be from left to right. You cannot, this is a complete binary tree, but this cannot be a complete, you cannot call this as a complete binary tree. See here. Is this a complete binary tree? No,
No,
because
ma'am.
if nodes are present, it should be from left to right. Your left node is missing, but right is there. So this cannot be a complete binary tree. This is your complete binary tree. Last up to last but one level it is complete, and the last level will be from left to right. In the last level, the nodes will be from left to right. So this becomes full binary tree. Okay, which is full till the last level. So binary tree or heap is essentially a complete binary tree. That means that you need not have nodes. The last level can be incomplete. That means that last level can be incomplete, and provided that nodes should be from left to right. Okay, so this is our binary tree, full complete binary tree. So heap is a complete binary tree. Okay, what is the one more requirement? So first requirement is that it should be essentially complete, and you know what is meant by that. The second property says that there should be parental dominance. What do you mean by parental dominance? The name itself, once you look into the name, you by yourself can guess what could be this parental dominance. What is this parental dominance? Who is the parent here for these two? Who is the parent for these two?
Root node.
Root node. So parental dominance means what? If at all, if see, it's defined as a binary tree with keys assigned to in nodes. So you will have keys assigned to this. So if keys are assigned, parental dominance means you should whatever level it is, if you take, yeah, if keys are assigned, the heap is a tree in which there will be parental dominance. It's a essentially a complete binary tree, yes, and also there should be parental dominance, and which means that the key which is at the parent position should be greater than the values of its children node. Got it? The key at each node is greater than or equal to the key at its children. It should be greater than or it should be equal to the children node. Understood what is a heap now?
Yes, ma'am.
Yes, ma'am.
Yeah. Yes. Okay. So a heap is essentially a binary tree with keys assigned to its nodes with the following following conditions which needs to be met. What are those conditions? It should have a tree shape, essentially a binary tree, complete binary tree. And the second is that there should be some parental dominance, which means that the key at each node, if you check any tree, so if you take this tree, here also parental dominance should be there. If you take this tree, parental dominance should be there. If you take the whole tree, then also parental dominance should be there. Okay, key at each node is greater than or equal to the key at its children. Okay, so that is your heap. No confusion with heap now. So some of the properties. So let us discuss some of the important properties of this heap. Important properties of heap. Sorry. The first thing is height. The height of the complete binary tree with n nodes is equal to log n. So height of this tree will be log n. So height of a complete binary tree with n nodes is log n. And the second property states that the root of heap contains the largest element. That's obvious, isn't it? When at each level, this should be the parental dominance should be taken care, then it obviously means that the root will have the highest element. Otherwise, how can you have a parental dominance? Because once you take this, these are all subtrees for it. So this should be greater. all the elements below this root should always be lesser than or equal. There can be lesser than or equal values when compared with this root. So root should always contain the largest element. And the third property is a node of a heap. A node of a heap, whenever it is considered, when it is considered with all its descendants, that is also a heap. Is also a heap. This means that any subtree, if you will consider, that is also a heap. That's what. Here, if you consider this should also be a heap. Parental's dominant should be there. See, of course it is. If you take this here also, you have a descendants is also a heap. If you take this, all its descendants are also heap. Okay. And and a heap can be implemented as an array. So how do you can implement heap as an array? How do you place it in array? You'll record the elements in top-down approach and from left to right. So if you want to record this tree in the form of an array, then what we'll do is, see how we'll write. I'll just show you how we'll write. Very simple. So we'll write 11 first, then we move down and move to the right, left to right. So which is the next element now I should place if it is implemented as an array? The root should be first, then we should move down. We should move from top, down and left like this. Down like this. So tell me the values now.
8.
8. Then I should come
2.
down. Then again left to right. Yes. 2.
6.
6. Then
5.
5. That's all. This is how it will be implemented in an array, in the form of an array. If you want to implement heap as an array, a heap can be implemented as an array. How? By recording its elements in the top down, left to right fashion, as I did here. Clear? Okay. Is that clear for everyone? How did I record it?
Yes, ma'am.
Yes. I started from top. If you will take, we will take this. I started from top, moved down, then left to right. Move down, left to right. This is how you will record the elements in an array. So what is the position now then? So heap can be implemented as an array, in which case you will have elements recorded like this. If I take the index of this as 1, 2, 3, 4, 5 and 6. So this is your heap. Okay, I've recorded the elements. These are in index values. Now, some of the properties under this when it is implemented as an array. The first is the parental node. Because we will implement this, that's why you should know all these things. The parental node will be in, okay, I'll write down because we need to write something here. So under this, the first property is the parental node keys will be in first n by 2 position of the array. Okay. And the last n by 2 will be leaf keys. Okay. So first n by 2 position will be occupied by the parents and the last n by 2 will be occupied by the children node. Now let's check which are the parent nodes here. So if I take this array. First n by 2 position, what's the, or how many number of elements we have here? How many number of elements we have here? How many elements are there in this heap? Whatever I have considered. So first three position, first n by 2 positions means till where?
3.
First, up to 3
8.
we have all. Yes, that is till 8. That is 3. Position 3 and value is 8. So first n by 2 positions will be parents and next n by 2 position will be leaves. So we have leaves here and we have parents here. Is that clear for everyone? If you check in, if you look into this tree, it's the same. See here, this is also a parent and these two are the children for it. This is a parent, these two are children, this is parent and it has a child node. Now, which 3 elements are parents? 11, 9 and 8. Which 3 are leaf? 2, 6 and 5. So out of 6 elements, the first n by 2 position will be occupied by parents and the last n by 2 positions will be occupied by leaves. That is one of the property of a heap. Got it? Is this clear for everyone?
Yes, ma'am.
Yeah.
Yes, ma'am.
The second property says, so the left and right children of any particular node I will be in positions 2i and 2i plus 1 respectively. So the left and right child children node of given any node I will be in positions 2i and 2i plus 1 respectively. Let's check this now. I want to know the children node of 9. For example, 9 here. 9 is a parent node here, isn't it? So I want to know the left and right children node of I. I is equal to 2 here. So where should I find the children node of this node I? That is node 2 in position 2i and 2i plus 1. So I've taken I as 2, 9. I want to know where its children nodes are. How can I find it? By using this 2 into I. So 2 to is in fourth position and I plus 1, 2i plus 1, which is 5th position. Is it right? Let's check. 4 and 5th position. Let's check in the diagram. Yes, 9 children nodes are 2 and 6 and their position are 2i and 2i plus 1. Is it clear now? So these are
Yes,
some of the quiz questions which will be asked. Okay. So given any node I, if they ask you to find the position of a children node, it's nothing but 2i and 2i plus 1. Okay. Fine. Clear?
Yes, ma'am.
Yeah. What about others?
Yes, ma'am.
Yes. I want
Yes,
more
ma'am.
answers. More yes. More replies. Okay. So if you are given with any node and you are asked to find its children node where they are, you should just say they are in position 2i and 2i plus 1. So the parent of a key in position I. This is, they'll give you parent node and ask you to find the children node. This is the way. But if they give you child node and they ask you to find the parent, then it will be in position I by 2. If at all, if any parent is, any children node position is given, I'll say, let's see here. Okay. So I have, I'll give I as 4 and I ask you to find the position of the parent of this. This is a child node position, find the parent. So you should say I by 2. Okay. So what is I by 2? 4 by 2, which is 2. Is it right? Yes. If you have an odd number, then it means that it is right child. That's all. Okay. Okay. If you find one child, easily you can find the other child also, not a problem. If you are given with any child, you can find the parent. Fine. So this is how what it says, if given the child node as I, the parent will be in position I by 2. So this is the child position given, and how to find the parent? It is I by 2. I by 2 or I by 2 plus 1 for the odd child. That's what it is. Okay. So all these things are clear, because now we'll start constructing a heap. Are these things clear? Okay.
Yes,
I'll
ma'am.
tell you. I'll revise it once again. So we are discussing the topic heap and heap sort, wherein we have just discussed what is the definition of a heap. That is, it's defined as a binary tree with keys assigned to its nodes. And what are the requirements for it? It should have a tree shape, and it should be essentially complete, and there should be parental dominance. What do you mean by parental dominance? And you know what is a complete binary tree as well, which is complete till the last but one level, but at the last level it has nodes from left to right. Parental dominance, the key at each node is greater than or equal to the key of its children, which means that the parent is always greater than its children node. So what are the important properties of this heap? If height of the tree is n, then if there are n nodes in a tree, the height will be log n, and the root always contains the largest element. And the node, if you consider any node, descendants will also form a heap. And you can implement a heap as an array, and we have implemented this example tree only in the form of array. And once it is implemented as an array, the first property is that parent node keys will be in first n by 2 positions, children node will be in next n by 2 position, and the left and right children node of I will be in position 2i into I plus 1, because you know all these things. These are discussed in DS already. The left and the right children node of I will be in position 2i into I plus 1, and if at all, if child position is given, you can find the parent position easily. It is I by 2. Clear what this means? We can move to constructing a heap for a given set of elements. There are two methods, and we will discuss both the methods. Is it clear?
Yes, ma'am.
Clear? Others? Can we move on?
Yes, ma'am.
Yeah, can we move
Yes,
on?
ma'am.
Yes. Can we move on to the construction of heap now then? Okay, we'll start constructing a heap. Okay. Yes. So constructing a heap for a given list of keys. Very easy if you will follow. Isn't it? Everything is easy if you are able to follow. So the first method is bottom up heap construction, and the second is top down heap construction. So how many methods do we have to construct a heap? We have two methods, bottom up and top down. So let's move on to bottom up first. So let's consider this bottom up heap construction algorithm. Fine. Yes. So what are the steps in this? So first what it does is given the list of keys. Okay, follow now. Listen to whatever I'm telling carefully. Given a set of elements, we just initialize the binary tree with n nodes by placing the keys in the order whatever is given. In whatever order the keys are given, in that way we construct the tree first. And then we will heapify the tree starting with the first parental node and ending with the root. So we'll start with the last parental node and then we end with the root. And at every step, the algorithm will check whether parental dominance holds for the key at that particular point. If the parental dominance is not holding, then we will exchange the keys. And then after completing the heapification of the subtree, we'll move on to the same node with predecessors. And the algorithm stops when it is done with the whole tree. Let me take an example and explain for you. Sorry, then it will be more clear. If I'll just keep telling, it's of no use. So suppose you are given with elements like this: 2, 9, 7, 6, 5, and 8. These are the elements. So what does the first step says? We'll just construct a binary tree with these with n nodes, with these 6 nodes, by placing the keys in the order given. So let's construct a tree in the order given. So first element, then left, then to the right, then to the left, then to the right, and later to the left of this. So first step is this. So it initializes the essentially complete binary tree with n nodes by placing the keys in the order given, and then it will heapify the tree in the way I'll do it now. So it will start with the last parental node. This is the last parental node. Okay, so we'll check this first, whether parental dominance holds good here. Is the parental dominance holding good for this tree, whatever I've taken here? We are starting from the last. We should always start from the last parental node. So this is the last parental node. And you're getting how this is the last parental node? Which are the parents here? 2, 9, and 7. Leaf node 6, 5, and 8. So this is the last parental node. So this will be parent position and this will be leaf node position. So this is the last parental node. We'll take the last parental node and check whether parental dominance is there. Is parental dominance holding good here? What do you mean by parental dominance?
No, ma'am.
Yeah. So parental dominance, what it means? The parent should be greater than children node. If we will look here, the parent is 7, child is 8, and there is no parental dominance holding good. So what can we do here? We can just heapify these two. Yeah, if it does not, we will exchange the node's key with the larger value of its children. If you have one more value here, there is no other child. Others, mute yourself. See to that you will mute yourself. So if you see, don't unnecessarily unmute. Okay? When I'll ask, you will not unmute. Whenever you wish, you will unmute and you will disturb the class. Okay? So once you find that, you should compare with both the children node. If there was one more node, we would have compared with both. Sumit? So if you have a parent, if you will check and you'll exchange with the greater children. Suppose you had one more 9 here. Then we would have exchanged it with 9. As we have only one child, we are exchanging these two. Okay, so that's the second point. The algorithm exchanges the node's key with the larger key of its children, and again it will check whether parental dominance holds good for this whenever I'll exchange whether parental key holds good. Let's do that first. 2, 9, 6, 5, 8, then 7. Okay. So why did we exchange this? Because parental dominance doesn't hold. So we exchanged 7 and 8. After that, we are checking here. After exchanging, we should again check whether parental dominance is there. Is it mismatched anywhere? Okay, there is no problem. Next, what do we do? After this, we'll move on to this child and check whether parental dominance holds good here. We check with this tree. We'll move like this. Okay. So next parent, 7 over. Now we'll move on to 9. 9. Check whether parental dominance holds good in this tree. Am I audible?
Yes, ma'am.
Yes, ma'am.
Yes. Parental dominance is there here?
Yes.
Yes.
Yes. So we need not have to exchange anything. Okay. So parental dominance for 9. Parental dominance for the key 9 holds good. So we will just move on. Now, you should show each and every step in construction. So we checked with these two elements and we got this. Parental dominance holds good for key 9. Now, let's move on to the next step here. Here, 2. Next parent is 2. We'll check. Check here. 298. 298. Is the parental dominance holding good here?
No, ma'am.
Yes. Now we have to exchange this. 2, 9, 8, 6, 5 and 7. So as there is no parental dominance doesn't hold good here, we have to exchange 2. It has 2 children, so 2 should be exchanged with its larger key children. Okay, not with 8, with 9, because 9 is the larger value, because always the parent should be greater than both the children node, isn't it? So we should exchange it with the 9. With 9 we should exchange. Let's exchange. So why are we exchanging here? Because parental dominance doesn't hold good. For this, I have highlighted this here. Arrow mark, whatever I have shown, their parental dominance doesn't hold good. So we are exchanging, hence exchange 2 with its larger key child. We'll do that here. We'll do it. So we'll place 9 here and we are placing 2 here. 8, 6, 5 and 7. Check now. Once we have done this, you should always, after completing the heapification of a subtree, see here, after completing the heapification of the subtree, at the current parental node, the algorithm should proceed to its immediate predecessor, that is this one, predecessor, and check whether it is holding good with its subtree as well. We have exchanged here. Now you should come to this and check whether here also parental dominance holds good. Is it holding good here, parental dominance?
No, ma'am.
No, see, it has changed. Hence, again, we have to heapify this. So what's the next thing? As we have checked with the subtree, we have found out that there is no dominance here and we are exchanging this. Okay, and I'll write down here 9. So these are the steps. This resulted with this resulted with this resulted, and here I am writing the next one. 9. With what I should exchange now? 2 with which value?
6.
Yes, because this is the larger value. 2, 5, and 7. After exchanging, we should check. No, there are no traces. This is the end. So it means that we have completed constructing an heap. This is the final tree. This is how the heap is constructed by using bottom-up approach. Clear? Clear for everyone?
Yes, ma'am.